Wow. Okay, so for the notes, I'm still in the middle of fixing some typo prepared by Wen Chan. That's why you see me updating the note. So what are busy things now? So busy things now is I have to mark your assignment. Can someone close the door, please? Yeah, I will mark your assignment 3. Your 4 is it extended? Okay. So I'll try and mark your assignment 3, and then I need to finish the exam writing. Then have to prepare lecture note. Okay, one more emergency one more up there. More pressing one is your tutorial. Yeah, I try to organize. How many weeks already? I think 2 weeks. The 2 weeks I haven't come out with tutorial. Yeah, I will put it up. Uh, what else? So this afternoon we have a seminar. Okay, so please come. 3:30. Where's the venue? Where's the venue? Yeah. Where's the venue this afternoon? G06. Which block? A4G06. So I request him to speak at the undergrad level, so you can try and see if you can follow. So after that we'll go for dinner. If you have time, you can join. And what else? Oh, right. So this week we have a group meeting, right? Okay, so please make sure if you have other arrangement, let me know. Otherwise, we just follow your own timing. Okay, so is your group fixed already Tuesday? Not yet. Okay. Yeah. And then one more thing is about Chiwi. Chiwi, you have to promote your thesis defense or not? No. What's your topic? What's your topic? About deformation on singularity. So you are resolving singularity, right? Are you resolving it? We make it a smooth. Right? Yes. Okay. What time is it? It's 4:30. Huh? 4:30? 4:30. Which day? Wednesday. Wednesday, what's the venue? F4104. Okay. So if you have time, you also can come. His stuff is very related to this stuff. Which we are going to enter now. Okay, so where did we stop last week? So last week we stopped at introducing blow up, right? We're introducing blow up, and what's the main surface we look at in blow up? What is the tilde linear we look at? Okay. You still remember? There's a blowout of the surface, right? Okay, so what's the blow up? Where does the blow up live in? The keyword here is a product set. Okay. The quasi-projective variety. A2 cross P1. Okay, so A2 is the surface. Okay, P1 is the extra dimension we have. Extra dimension we have. Do you remember what's the extra dimension we add in? Can you summarize in a word? What's the extra dimension we add? Okay, let's say we blow up on the origin, right? At the origin. Okay, so we look at all the line pass through the origin. Okay, and then how the line split up in A2 cross P1. Split up by what? By the gradient, exactly. Okay, so if you can imagine, right, y equals to x line, y equals to kx, for example, okay, in your calculus, how many k you could have from negative infinity to infinity, okay, not including infinity. Then this form real line. So that's why you have this picture here last time. It's a picture. The picture got. Okay, good. Such a people. Okay, so that's why you have different direction linear lines in different height. Okay, because these are the gradient. Okay, now does it make sense? Okay, so it's really a subset of A2 cross P1 here. Why? P1 is the vertical part, A2 is the horizontal part. Okay, so you can imagine that this P1, right, this E, right? Still remember what's this E? Is a pre-image of the 0 point. Okay, so pre-image of 0 point is what? 0, 0 cross the whole P1. Okay, so this is the whole P1 here. Okay, and then I mean product set, right? How do you imagine product set? Right? So at a point at P1, you attach a whole A2. Okay, so actually these lines are picking a line from the each A2. Okay? The direction will follow the gradient you have for your P1 column 2. Make sense or not? Does it make sense? Okay, so actually your blow up live inside a so-called 3D space. Okay, it's a 3D space actually. So you should imagine that every P1 here there's a A2. Okay, and then you are just picking out a line from that A2. Make sense? Make sense? Okay. Actually, A2 cross P1, how far is it from A3? How far is it from A3? Sorry? Sorry? Understand. So my question is A2 cross P1. How is it different from A3? Yes. So you should compare your P1 to A1. How does it how do you compare P1 to A1? I still remember when we do the projective geometry. P1 can be split into what? A1 plus infinity. Okay. If you like, you can imagine actually this P1 here could be joined together. If you like. Maybe I think you could simply think it as a cylinder. You could think of it as a cylinder. Okay. Yeah, blowing out towards cylinder surfaces. Okay, make sense? Must make sense of this picture because next chapter is all about this. Okay, let's try do one concrete example. Okay, I know that you like concrete example, right? Let's do one. Okay, so let's now we consider this curve here. Okay, let's consider this particular curve here. Let's call it C. This is a zero set of y squared minus s cubed minus s squared. Okay, anyone know what this curve looks like? This curve looks like. Yeah, this kind of thing, I think you can throw into AH as the first year to do it. Okay, so how this curve looks like? This curve is like this. I think I'm pretty sure you guys see this at some point. Maybe in the parameterization way, and not in the basic function way. Okay. Well, okay. Okay. So let's say if we want to blow up the surface, okay, but blow up at the origin, right? We blow up the whole surface. But let's say now we want to just look at how about the inverse image of this one. Okay, do you remember the dragon, the flying dragon I showed you last time? Then let's see how this dragon here. So in this case, you might see that dragon is a 3D thing, right? You make it move in 2D here. And then if you want to go and return back, right, cycle back, right, then because it comes from some infinity, right, it must self-intersect itself. Okay, it must be itself. I mean, beaten itself, something like that. Okay, you must have self-intersection. Let's see what can we do. What happens if we do blow up? Okay, on this curve here. Okay, right. So let's consider the inverse image of the C here. Okay, so the blowout of this guy live in A2 cross P1. Okay, so this is a A2 coordinate and P1 coordinate here. Okay, satisfy what equation here? There's one you have to satisfy first, right? For general blowout of the surface. What is it? Something tells you about this four coordinate here. To make sure we have the exceptional fiber. Still remember? We cross multiply the coordinate. So T0y equals to T1x. Okay, but now we just want to look at specific x and y. Okay, so this specific x and y have to satisfy the zero set of y squared minus s cubed minus x squared equals to 0. So we'll try and understand this log. Okay, so let's see how should we understand this. Okay, first of all, not that. If you look at the affine covering of P1, okay, here, okay, which is U0 union U1. Okay, do you still remember what is U0, U1 here? Do you remember? These are the open set. Okay, so meaning what? These are the UI such that Ti not equals to 0. Okay, when Ti equals 0 is what we call the hyperplane. So the complement is the hyperplane. Okay, this one is on P1 and that line, if you still remember. Okay, the line there. So you might be a bit confused why line got U0, U1 here. So actually this U0, U1 actually live in the description of A2. A2. So description of A2, right? Still remember what point okay. So so for U0, right, it doesn't cover T0 equals to doesn't cover T0 equals to 0, right? So if T0 equals 0, what's that point on P1? What's that point on P1? If you use the gradient, it is the point of the 0. Okay, so for U0, that's the point that U0 didn't cover in the P1. Okay, so maybe let's draw it. So let's say we already view P1K as a line, right? So this is the this line U0. But U1, which point did it cover by U1? Sorry, this one U1. U1 cover everything except the infinity. Make sense? Okay. But we didn't draw infinity point anyways. So unless maybe we want to like close it, maybe 0 is here and then infinity is here. Then it didn't cover infinity. Okay, so these two together will cover the whole P1. Make sense? Any question? Okay. Okay, so then by using this covering here, oh, this is U1. then what we would cover here. Then we will induce the two covering here for our blowout surface. Let's call it V0, V1. Here we will define this, no worries. I haven't defined for you. Such that I live in A2 cross A1, okay, where V0 is all the point. It's all the point. I'm not sure why I solved this T1 and T0. Let's see if we have any problem or not later. Let's keep it this way first. Such that T0 is non-zero, and if T0 is non-zero, then you can require your first function to be all divided by T0 at least. Okay, and on the other hand, we'll do a similar thing. Okay, such that T1 is non-zero, and then the curve that I look at is just x minus y T0. Okay, does it make sense? If T0 is non-zero, then we can divide by it. If Ty is non-zero, we can divide by it. Okay, so it's just look at the specific part of that curve. Does it make sense? Is it clear that why this will cover the whole thing? Is it clear? Is it clear why this will cover the whole thing? If there's something that's not covered by V0, it should be in V1, right? Okay, if something that's not covered by V1, it should be in V0, right? Okay. Any question? Feel free to ask. Huh? I don't want you to stay confused forever. If you want to stay confused forever, you might as well you go back read yourself. Okay. 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 So as a side note here, actually, what did you see here? Actually, this V0, V1, right? Actually, are isomorphic to A2. Okay. So from now on, that U equals to T1 over T0 and V equals to T0, T1. Okay, so that we don't need to write this fraction every time. And actually, this is a very good notation whenever you want to do blowout or some other things. Okay, because it will simplify the writing. All right. So what do we actually see here? Okay, actually, what are we seeing here? So this is covering for the whole blow-up surface, right? So now we're gonna see what happened. We just look at the pre-measure of this curve here. Okay, so exactly we want to pick up the point on that rotating staircase like that, right? And let's say that it's a rotating staircase, which is the blow up of the surface. So now we just want to look at the blow up of the curves. Okay, so if you try and intersect it, let's see what happened. So look at I must see. Let's say easier. Okay, let's see what happens here. Okay, so the claim is okay. So if you bound to this, condition here, right? Bound to this condition. Okay. Do you want to write it down? try and write it down. Write down this equation, all of you. Okay, you cannot do on your head. Try and write down this equation. Okay, these two equations here, and then write down this equation here as well. Okay, have you tried to copy down? Yeah, some practical. Try and write it down now. Yeah, you go back, you don't know what to do. Okay, set this, write these two, and then write these two. Okay, so intersection means these four have to satisfy, right? Okay, so convince yourself that I can reduce this set to U in V naught, which is isomorphic to the okay here, such that you just need to satisfy x squared of x plus 1 minus u squared. Okay, do the substitution. Can see? Can see? We no need, there's no more. So we still have T0, T1, right? But y gets substituted already. Okay, make sense? Does it make sense? Okay, because in particular this one, this one is useful here because T0 is not 0 already. So you can write entirely y in terms of T1 over T0x. And then you substitute. Okay. T0, T1 is still there, but we hide it inside U already. Make sense? Okay. So similarly, what can you think of? You can do another thing, right? So you could intersect with B as well. So if this time here, instead of leaving x, right, you will leave y. Okay, and then the equation becomes y squared. Q. Make sense? Okay. So these two are perfectly good curve, right? Very good curve in A2. But how to put them together? Okay, how to put them together here? Okay, so not that we didn't look at the pre-mesh of 0, right? Still remember or not? Pre-mesh of 0 is always that exceptional divisor. Okay, so this is other than the exceptional divisor. Okay, this. Okay, so if we're gonna look at the whole pi inverse C, right? Okay, so what we are looking at is actually the closure of this thing. Okay, we're actually looking at the closure. At this curve in A2. Okay, and then we denote it by C tilde. Okay, so if you learn algebraic topology before, right, you could think of this C tilde as a lift. It leads to a larger space. Okay, it's a lift, yeah. So we call it a C tilde. Okay, we look at the pre-mesh and then we complete. Does it make sense why I look at the completion of the closure? So if you look at the previous picture, okay, last time we talked about, let's say we have a curve like this, right? It will get lifted up, okay? But if you look at the whole pre-image, right, actually you are getting this curve plus this whole divisor, but this is not what I wanted to see. What I wanted to see is after I lift this curve, where it intersect. Okay, I cannot say intersect. Then can you accept I say limit or not? I think it's not rigorous, but it's a way to describe it. So it's like okay, precise term is closure. Okay, taking the closure. So meaning you see if you have a line like this and then the other line should go. Okay, I really want to use limit here. So left limit and the right limit is the same, right? And so after taking a closure is this. Okay, instead of taking the whole divisor. Correct? If you take, if you purely take, let's say, pre-mesh of this line that passing through origin, right, you will get the whole exceptional divisor. But this is not with 1, 4, C tilde. Okay, we just want to look at the pre-mesh of C, take away the point and then take a closure. Make sense? Okay, I think just now I missed out something, huh? Is it? Did I miss out? Yes, missed out. So I guess this one is the closure of C. Huh? Yeah, yeah, yeah. Okay. Okay. Then I think this is not well defined. Then this guy here. Yes, I think this one also need to be written. Okay, make sense? Okay, all right. Yes, this function is a Zariski function. Is a Zariski. You want to make it a closer. You don't understand what I said just now. Just now I already said this is not precise thinking already. The point here is if you make that true, you can. Yeah. You say you don't understand my assumption just now. So why I said just now limit is not precise here because I didn't link limit to this Zariski closure, right? But if you see from this picture, right, is it obvious to you that there's only one point you need to fill it in to make it close? Yeah, I think another one is at the infinity but that one is covered by this inverse already. Infinity is covered by this inverse already. But the problem is we throw away the origin. Does that make sense? Okay. Yeah, I should think of a way to talk about this precisely. But to precisely just taking a closure. I think I can talk about limit in terms of limit point, Zariski topology, not the epsilon delta. Yeah, I think I can talk about limit point using Zariski topology. Yeah, then the limit point makes sense. Okay, it's not the calculus limit. Maybe it prompt you to calculus two limit. But actually, can I say that I'm not far away? Zara, which one is more? Which one is closer? Which one is? Let me think. Which one is finer? Uh, Euclidean topology is fine. And Euclidean topology is fine. Okay. Well, so how to find this closure? Okay, out of no blue, we want to find this closure. So first thing to note here. Okay, first thing to note here. Actually, this C tilde should live in B0. Okay, actually it lives entirely inside B0. Still remember what is B0? B0 is where the second coordinate of P1 is non-zero. This part is non-zero. But if you look at our curve, what can you observe here? So if you look at our curve here, our y actually can be written as plus minus of x times square root x plus 1. It's true. You play around with that line curve equation. Yeah. Okay. So meaning what? That y there, right? When you go to the 0 point, it's really is well defined. Okay. But if you do it the other way around, actually it doesn't quite work. Okay. If you do it the other way around, it doesn't quite work. Okay, if you want to express s in terms of y, that's what I say. Okay, it doesn't quite work. Okay, so you can see that all these y live inside V0. x1. Okay, you mentioned x1 leaving inside. X leaving inside v0 and y leaving inside v0. Okay. Okay, so is it time for me to draw it? Yeah. So if we lift it up, okay. Okay, so if we lift it up, how should we imagine this line here? Let me think. So your positive gradient is a higher point, right? Okay, so positive. So okay, let's see how your gradient change. So okay, so let's see. Yeah. So how your gradient change from positive to negative, negative here, right? Right. Okay, negative, and then go straight again, and then positive again, and then negative again, and then negative, negative, negative. Okay, so you actually go from top to bottom. I don't know. Wait, let me think. Is it correct? And we turn back, right? So we positive, and then go to infinity. Yeah. Wait, let me think. Yeah, okay, wait. So, okay, I think I'm a bit confused. So let's draw all the line up. Then it will make sense. So last time I told you, right, the pre-mesh of this plot is um, just the pre-mesh of this line. Okay, I think I count it differently. I use the, the projectivization of the tangent space, but I think that's not the case. Okay, so what can we see is these points here are living on a positive line, okay, positive gradient line, and then these are still positive, but the positivity decreases, correct? Because these points are living on the lower gradient line, okay, and then up to here, this is a zero gradient line, okay, makes sense, and then go to the negative line. Okay, so it's positive, slowly positive, reduce up to zero, and then negative. Okay, so from here, what you should see is positive decreasing, okay, and then up to zero, and then going down. Okay, and then this turning point here is the 0, 0, 0 that Adrian asked me after the class last time. So this is the 0 point. Yeah, 0. No, not quite 0 point, is this point here. So what's this point? Anyone know what's this point here? I think at your level now, you should know how to find this. What's this point? This is a y intercept of x intercept. X intercept. Find out, 不要等我，很早，等我做梦。Yes, good. So this is a -1, 0. Okay, so actually this point is a -1, 0 with the 0, 0. Make sense? Okay, and then go down. You have to go down. Sorry? Huh? Oh, sorry, 0, 1 again. Okay. Yeah, there's no 0, 0 there. Okay, so after you make that point, then you go down. Make sense? Okay, can see a difference or not? Before blowout, after blowout. Then one you intersect yourself, and the other one you go from top to bottom. Make sense? Okay? But you see, but what's the difference of what's the difference between this picture and the previous picture? Okay, maybe not apparent now. Let me draw more apparent. So one will go up, and then we should go down. Okay, so what you can see that is the intersection at the origin split. Is split. Split. Yeah. So maybe you need to go up. Actually, you can find this point, right? You find it? Yeah, you can find it, right? So what's that point? Find it to make sure you understand why am I drawing here. Find it. This is a calculus 2 question. This is 0, 1, is it? 0, 1 with 1, 0. And then the other one? Yes. Huh? 0 minus 1. You guess. What do you mean by you guess? Why can't you calculate? I thought you're a mathematician. Why you guess? Okay, the problem is mathematician too lazy. Found the problem already. So this is the how to find this point? Do you know how to find this point here? How to speak? Yeah. So yeah, sure. Sure. But what's the no? Well, I mean, wait, before that. Wait. So on xy, it shouldn't be 0, 1, right? It should be 0, 0, right? Okay, so this part should be 0, 0. Right. So now you need to figure out what's the tangent, correct? That's right. True. Okay, true. You need to find what's the tangent there. Okay, so wait. Huh? Okay, good. So now let's work together. Find this tangent now. Okay, let's work together and find this tangent here. Okay, so what's this tangent here? You already see that this is intersecting with the exceptional divisor here, which we call E. Okay, so if we want to look at C prime, take away the rest of your line. Okay, which is C prime just intersect with E. How do you do the computation here? So based on this assumption here, we just let xy to be 0, 0. Okay, and then the equation that governs this v0 is what? X squared times x plus 1 minus u squared. We can find the closure point here. Okay, and then if you sub x equals 0 in, you get 1 minus u squared. And then what do you get here? Actually, you get u squared equals to 1, which means u equals to plus minus 1. So there are two possibilities here. But what is u? I still remember the change of variable we did here is t1 over t0. Okay, so if you put back the t0, t1, right? Okay, so one choice you can make is 1, 1. Don't ask me why not pick minus 1, minus 1. It's the same point. Okay, similarly, the other point is 1, minus 1. Okay, don't ask me why don't pick minus 1, 1. It's the same point. Okay, 不要这么执着，好不好？ Okay, but what happens here is this is exactly the gradient of the point. Okay, if you use the usual calculus dy dx to compute it. Okay, it's a true gradient. So meaning what? After you blow up, you get the gradient without doing decision. So analysis away already. Okay, 打包送走。Okay or not? Okay, so actually these 2 points these points correspond to the two tangents. And let's call it L11 and L1 minus 1 to C and the origin. Okay, so if I like to bring that picture down here, how about I just draw it on the spot? So do it on the spot here. Okay, then if you go and compute your two tangent line, I think this is one of the example in calculus 2, right? I remember, I guess. If not, it's in the assignment. I think I remember. Use the parametrization, horizontal tangent, vertical tangent, whatever like that. Right? Then prove that there's only a few tangent, these are the tangent. And then, do you remember I'll do this? Do you remember? Give you few tangent and then ask you work out the space curve. Okay? Yeah. I remember because I did this question 3 times. Right. Okay, so these are so when you lift out the intersection at the P1 tells you the gradient at that point. Okay. So the claim here is we won't prove it, but I think hopefully it's the next section. Okay, this is the last bit from last time where I want to show you there's really something meaningful we do with blow up here. So the claim is this pi inverse C, right? Okay, in this case, I think they include the whole E here. It's not just the CQ that the whole straight line plus the lift here. Okay, actually is something we call smooth. I haven't defined for you what is smooth, but smooth in a differential manifold should be infinitely differentiable. Okay. Okay. Then we call CQ the strict transformation, strict transform, or we call the resolution. C. Okay, and then the another claim is CQ is birationally equivalent. Okay, so meaning the function field you define on this resolution actually is the same. Okay, isomorphic, same in terms of isomorphic, isomorphic to the original C, the function field of the original C, but it most probably is not isomorphic. Isomorphic here means as a function, as a polynomial, as a coordinate ring. Okay, it's not isomorphic. Make sense? Any questions? So this birational equivalence, still remember or not, is given by the rational map. Rational map might not be defined at every point. But isomorphic here, you require it to be a polynomial map. Okay? You cannot do that. Okay? But you can find a rational regular. Okay. I think for now, you can go and dig Chiwei abstract. I think you can understand the abstract. You can dig the abstract out. See, you understand what he's trying to prove to you. Okay. Any question before I take a break? Well, one example, take out 1 hour. So you see, that's why lecture don't want to do question in class one. Too many things to explain. Any question? We haven't defined what is smooth yet, so please don't ask me. But what you need to know now is a very nice thing, nicer than previous, nicer property. Okay, and then you should be hinted with the tangent line. There was something to do with the tangent. Okay, any question? Yes. I don't know. Actually, I don't know. Have you tried to blow up it again yet before? Have you tried to blow up? You mean you want to blow these things out, right? Let's keep all the technical details. Okay, by the way, you can have a break now. We can continue discuss. Can break until 108. You mean this thing? Cups, like this. Cups. What do you mean cups?
More like this thing.
This one? This one is quite natural.
If it is like this, then I believe that it will be smooth. If it is a normal cast, it will be smooth.
This one is even easier, right? This one.
Then this one will not be smooth, right? The blow up.
What do you mean by smooth? Well, define smooth. Yeah.
Well, not even smooth, not even continuous actually.
Why?
If we remove the origin point, because this has
Oh.
the input point have different gradients, so therefore they will come out from different points of the.
Let me think. So, okay, this. So I mean this gradient is the being the same, right?
Yeah.
Let's say this one is 1, this one is -5. And then I think I get what you say.
Continuous.
So what's the Zariski closure of that? Do you have idea?
I'm actually not sure. This is just more like an intuition, but I cannot exactly.
Okay, let's try. So you got M1 equals to 1, right? So this point is huh? 大家给我想一下 should I write the formula of this line first?
X equals 1.
So this is a piecewise thing. Yeah, y equals to x, where x is greater than equals. Wait, this is not a function. This. So change to this direction, like this. Yeah, absolute value. Yes. Absolute value, correct. So let's see. Let's see how should we do this program here. So
其实我也不会做，我也感觉不一样吧。都是你应该不 continuous 的。
And then let's see.
应该是这样的，应该是这样。应该是一个从正的负的到零，一个从正的到。
You mean like this?
Stay on one line。它只有2层嘛，有2个 gradient， 只有2层。
Like this.
有2层啊，yeah.
Like this.
Yeah, about like this.
But we want to take the Zariski closure, right?
Yeah.
So what is the Zariski closure of this thing?
Zariski closure.
Should be this, right?
Should be 2 lines.
This.
I think this is a lot.
Is this set close enough?
Zariski closure.
Yes.
I think this have to be close in. Yeah, right. Close in this place, right?
它是你要 Zariski closure 连成个无限。
I mean.
是
Limit point. Or actually, it's the whole thing. Maybe you need to take the whole thing. It's not surprised if you need to take the whole thing. Feel like you need to take the whole thing because you want to define a 0 set inside of P1. Be the whole thing. No, the claim is the exception. You see, this claim is not just C tilde is smooth. It's E plus C tilde. Okay. I think if you take closure, it need to be the whole E. But you need to show it. Yeah, I don't think. Yeah. I guess. Yeah, why I think of taking a whole line is because when I go to toilet, right, I think about this question here. Can I define the interval as a closed end. I don't think. Darcy closed end. Yeah, not a Euclidean. Yeah, I don't think so. So if you have a interval, right? Again, for Darcy closed, you need to take everything. Yeah, I think that's a very good question. Okay, you can think about what's the, for example, Darcy closure of. So how should I draw this? Can I use I one? Because I don't know what's the I. So let's say A, B. And then here I put a bar Z, directly close. Meaning you need to write it as a V of something. The smallest V of something. And then the claim is the smallest V of something must be the whole. A bit similar, like you showing the irreducible, classifying the irreducible variety, right? Ah, right. We did show in class, right? All the irreducible in A1 is what? Are the finite, are the not finite, or are the singleton, right? Or the whole line. Yeah, you should refer back to that proof. All the closed set is finite. Oh yeah. Oh yeah. 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 That one is building on what we know. Or you want to show from scratch also can. From scratch. Like show that these are equal. I mean, like without using the result. Yeah, sure. Okay. Yeah, can try and do this. Probably can try and find the ZRC closure of the interval. No matter it's open, close, or half close, half open. They have to be the whole. So one suggestion is using the classification we know, Zariski topology classification of A1. Hey, when do we have break just now? 48.
如果周四下午的朋友这课之后1个小时可以。
周四下午还几点
？5到6。
这么迟？
可以吗？
可以是可以吧？
但是我们主要其他时间我们这边也得来协调。
OK，
那就周四。OK。
去周三如果早一点其实可以，我 free 啊，6点到8点的时间，你们不 free？我已经看完全部 episode， 我还没有学到。
这次这课之后，那我们得晚。
得晚。
因为他们突然间上到8点15分钟。应该上到9点，我们7点进。
对啊，周四啊。周四如果 before class， 周四是几点上课来的？如果2到3呢？Okay. Okay, let's start a new chapter. Okay, so if you lost in the previous chapter, it's okay, but we are going to start new chapter now. So please wake up. Okay, so in this chapter, we'll talk about smooth points and dimension. Okay, so we decided to put dimension here. So far we are still following clouds or mouse rate. So you can continue refer that book. Unless I change, I will let you know. If not, we just continue with that book. You can read in advance. Okay, so first thing first, we're going to define a smooth point on hypersurfaces. Do you still remember what's the definition of hypersurface? Larry. Good. So why is it the basic things we look at here? Because it's a zero set of a single problem. Don't care what is the degree one. Don't care. The point here is only one f inside the v. So we call it a hypersurface. Make sense? So hypersurface is the easiest variety you want to look at. Okay, with zero set of one point. I don't care what's the degree one. Okay, I don't care. The problem here is only one f inside there. Okay, the tangent space of the hypersurface. Okay, and then we'll generalize from here. Okay, so in that case, let our V be just one VF, okay, where F is irreducible. Okay, irreducible. Okay, such that V is also irreducible. Okay, so if your ideal is principal, irreducibility prime is the same at maximum. Is it? Try and recall it. Okay. I think I put it as a tutorial question. Okay. So let's say our V is defined by a single function zero set. And then what's the tangent space here? Okay, so I want you to click inside your mind. What's this tangent space here? Okay, if you're not gonna to click, you're lost all the way. So what's the tangent space? To this V here, okay, hypersurface at a point. Okay, so we always define this the tangent space at a point first. Okay, so we'll write it as TPV. Okay, so TPV. So you should ask, so where should I pick the point from? Okay, where should I pick the point of TVP here? Okay, so actually you are picking from the same point, same affine space for your hypersurface. Okay, same point, same affine space. Okay, although I'm speaking of the same affine space, actually it's the same. It's the same. Okay, maybe it's not apparent why it lives in the space, same affine space. But what this point has to satisfy is, if you look at the all the partial derivative, okay, so this one is really calculus 2. So you take your f, right? Your f is a polynomial in different x, y, z, like that, right? Then you can do partial derivative with respect to all these direction, and then you substitute your point into it. Okay, then I give you a number, right? Okay, after that number, you just multiply xi minus the I coordinate of the point. Okay, then I think this should recall you back the tangent space in calculus 2. In calculus 2, what we did, we only did two dimension, 3 or 2 dimension, 2 dimension, or 3, 2 or 3. So del f del x, right? And then p, and then x minus x1 plus del f del y p times x minus y minus y1 like that, right? Okay, 3 terms. Okay, so this is a generalization. It is an n dimension. Okay, I think no need to describe the del for you now. I think you understand. Okay, so everyone okay? Okay, now. Okay. Make sense? Okay. So from here you should see like this is a plane equation actually. So actually this is the tangent plane. So next part, what kind of space is this? Actually, this is a vector space. Where actually a bit slightly more than a vector space is called the affine subspace. It's not just a vector space, it's an affine subspace here. So what is affine subspace here? I think for those who went through Prof. Dio not strong analysis, right? You guys are asked to prove something. What's affine here? I think there's one student asked me about a question about affine, showing something. It's a affine ball or what? You still remember? You don't remember? I remember there's one student asked me about this affine thing. So what's the affine subspace here? What's the difference between vector space and affine subspace here? It just says that affine here is a translation, okay, of subspace. So meaning what? The origin is not zero anymore. That's it. Okay, so meaning if you translate the origin back, it is a vector subspace. Okay. Does it make sense? Okay. Does it make sense? Okay. So can you imagine why it get translated? Actually, from this line here, P is inside there. It is translated there. Okay, so can you see why P is inside there or not? What are the AIs? AI are the P, actually, right? So I don't care what partial derivative I compute. I put P in, surely I get 0. Make sense? Okay, so P is always there. Okay, P is always there. So what is B? P inside TPV. Okay. So then to prove that, what is an affine subspace here? So let me repeat the definition for you. An affine subspace means translate. Yes. 刮胡在哪里？刮胡在哪里？哦，刮胡啊！哦，thank you. I mean, 哪里？刮胡跟没有刮胡 actually 没有差别，只是我要不要刮胡？我不要刮胡吧。When I think about this, it's like I apply some operation on 2V give me another set, but it doesn't matter. Book 也是有啊。Yeah, I tell you why it happens. It's like construction. So you give me a hypersurface. This TP will produce you another set. Yeah, 没有一个解，有一个解。Anyway, okay, so whenever we put this, right, it's like a function, right? Okay, so you can imagine if I change different v, TPV will change. Right? So you can think of it as a function. Another thing, what else? 什么刮胡？什么刮胡条？哦，就是那个 OK. Alright. So since this is so to show that it's affine subspace, you just need to show that it's a translate of a vector subspace. You just so you can show that actually every point here, you can write it as a P plus something. Okay, for every point inside here, you can write it as a. Do you get what I'm saying? If there's an xi that satisfies this equation, right, you should be able to write those points as Pi plus P. Can understand what I say? So first claim. If xi, okay, so if let's say I call it x bar, x1, x2, xn, it satisfies sum of okay. So, let's say you will be able to write as like let's say or something. Try to show this. Okay. Once you can do that, you just need to show that T0V. T0V is a suffix, it's easy. So meaning when AI are 0. Yeah, so if you have point that satisfy this linear combination with 0, and then you add them out, you can do distributive, right, on this partial derivative. Okay, such that the sum is still 0. If you have scalar inside here, you can pull the scalar out, okay, to get the original equation. Make sense? Okay. And then I think the other one you need to show is just try to show this. Okay. On the variable, what do you mean?
Otherwise, F1 coordinate also the point.
Ah, makes sense. Okay. So we try not to clash with the direction. So let's say we use y. Okay. I guess another difficulty of this class is I cannot satisfy you always on the spot. Let me tell you one thing. Okay. Okay. You have to be self-satisfied. Okay. What I want you to make sure inside my class is not understand what I say, is to repeat what I say. If you can repeat, go back and think about it. If you think that it's wrong, you can come back and challenge me. It's okay. Okay, I don't see challenge as a bad thing. And I also hope that you don't see challenge as a bad thing. Not like, oh, 就是你的错，哇，就是你的错，给我抓到你的错，耶！ It's not like that, okay? Please be a mature person. Okay. I hope this is a new way to see mistake. It's not like, oh, I catch your weakness, I win over you. It's not like that. Okay? Right. Now you say not. Wait. This is an MI. Okay. Okay, why I call this an advanced course because you some of the simple calculation you have to do yourself. Okay, I cannot bring your hand, show you exactly everything detail, clear and white. Okay. So far, okay. You question about this? Okay. So for example, let me give you an example. For example, you don't believe my claim one, make a note here, go back and check whether it's true or not. If not true, you come back and tell me. Okay, not everything I claim is true, but you should at least start it as a hint. Okay, it's like the question I gave you in exam, right? If it's too hard, I'll give you some hint to start with. If you don't use my hint, okay or not? Okay, no problem. Okay, as long as it's correct. Okay, so sometimes student will ask me, 老师帮我检查那个步骤对吗 ？Actually, 你知道我在想什么 ？Actually, you know what I'm thinking when student ask me about this. What am I thinking? 你没有想过你老师在想什么在改你的考卷？你觉得他讲想啊？什么？垃圾？垃圾 ？No, I don't care. I don't care what thing you. I mean, I don't care what method you use. As long as it's correct one, that's okay. As long as it makes sense, okay. As long as it's logically defined, it's fine. Okay, so that's why in my class you rarely see I teach method one. Rarely, very rarely. If I teach method, maybe it's I don't understand already. You need to be worried already. Maybe I'm not familiar with the subject. So I teach you method. I'm gonna learn this. 其他不用管的了. You need to be worried already. So if I understand the subject, then that means what you can use whatever you want. As long as correct. As long as it makes sense. Okay. Makes sense. Please don't change. Even I know that in this school there's some cases there's authority. Okay, asking you that cannot use this. So maybe I tell you authority will get wrong. So I'm the one that challenge authority. Okay, I hope you can also because you are my student. I teach you how to challenge them. Challenge them not by like opposing them. I mean directly oppose. But you need to find a good way to talk to them. Show them the right way. But this part will be hard. Maybe you need to sacrifice it sometimes. Okay, but please don't lose to authority. Okay. Okay. Next lemma. Let's say we have a line, a fine line to P. Then P is a multiple root of F restricted to that line. Okay. If and only if L is in TPP. Okay. So for like the beginner, right? Whenever they see this kind of statement, then something or they subproof already, they forget to see the effect on it. Okay. So actually this then of this thing, right, is happening. Either one side is true. Okay. If you are a multiple root of F restrict to L, then L is a L live inside the tangent space. Okay, and P. Or L live inside the tangent space of P. Okay, if P is a multiple root of F. Does it make sense? One side true only, the other side true. It's not like P is always a multiple root. Okay. Any question? Okay. Okay. Should we prove this in class or not? You want to see this proof? Okay, I let Lydia decide. After decide, you cannot cry anymore. If you cry, you go out from my class. I don't care. You cannot cry in my class. You have to respect me. This is my class. More people, I will be more fierce than positive, I tell you. Okay. Please listen. Okay. So let's start from this line here. So this line has a parameterization. So what's the line? What's the parameterization of the line? What does it mean by line here? Line should be like, okay, for example, linear algebra. Okay, when you solve the null space, right? Okay, the null space is non-trivial. It's always what? It's like some free variable, right? Kind of vector. Okay, so if it's one dimensional, then it is a line. So meaning your parameterization is AI plus BIT. Yeah. So this BI here is a vector in the direction of L. Okay, what do we do next? So if we look at F restrict to L, what does it mean here? What do we mean by a restriction here? So meaning you just look at what's the image of F on this point. But I already tell you how to describe all these points. Okay, so actually we can further reduce the variable to T. Okay. So these are just F on A1 plus B on T up to AN plus B. So this is the restriction. Okay. So what do we observe here? If T equals 0, okay, meaning the X is the point P there. What do we have? We actually have G0 equals to FP equals to 0. Okay, so meaning what? Meaning P is 0. Is it correct or not? Let's see. Is it true? What is F? Yes, what is F? Still remember where this F come from? Where's this F come from? There's only really one F we are talking about here. Is the yes, the irreducible polynomial that define the variety. Okay, but the P is living on the variety. Okay, so meaning P is the zero set of P. Okay. Yes, similarly, T when T equals 0 is the zero set of G. Okay. So we are kind of like shifting P to 0. Okay, after we do this parameterization. Okay, so maybe you will ask why I want to talk about G. Okay, actually there's algebraic proof that maybe you need to write it out. Maybe you can call it a lemma here. So maybe you need to try and prove this. So together with this property, it follows that G has a multiple root at 0. Okay, if and only if the partial derivative of G with respect to 0 is also 0. Okay, actually here I don't need to put partial, I don't put the dg dt. And this one you need to prove. And this one you need to prove. That's why we write it as a G here, because this is a simple statement that you need to understand. Okay, if you evaluate at that point 0, first derivative is 0, and then G is a polynomial, then it should have a multiple root. So meaning what? Meaning the monomial x should appear at least twice. Okay, you should prove this. Okay, where so the condition is G is also polynomial. Okay, but if you write these down using chain rule, right? So using chain rule, relate back to F again. This is exactly the tangent space definition we have. Okay, if you apply a chain rule, okay. And if you satisfy this, this will imply that the point L is inside the TBB because it satisfies that equation, the partial derivative. Okay, does it make sense? Any question? 可以问啊，不要以为我很凶啊，不敢问。我觉得站在正常的情况里面呢，要求我是 OK 的。如果我一直放下身段了，你都不要接受的话，我实在真的不知道怎么办。我觉得我们大家都有难处了，all of us has difficulty。我觉得不是你难罢了，我也难了。他们说我也是很累，对，我可以哭吗？我要哭了，我要哭。不过我一直哭，我想叫。Similarly for you，你一直哭，你想学？Same question。那已经20多岁了，你要靠有40年可以哭，你还要哭？你进棺材你还要哭？解决问题？如果能的话，我也会过，你们也会了，可以解决问题吗？希望你们真的是听进去。OK。Okay. Okay. So, what's the important thing about this lemma here? Actually, it tells you that when is an affine line on the tangent space of V. When you restrict your f, okay, on those lines, it is actually a come with a multiple root. Okay. So the picture you should see is when you have the time p here, when you point p here on your variety, don't know where to see your variety, but if you look at the tangent space here, okay, and then there's a line, fine line pass through p that live inside this tangent space here. So how your variety looks like, how your variety looks like along this line here. Okay, how your variety looks like. It's at least degree 2 monomial. At least degree 2. Okay. So most probably okay, let's draw more lines here. Okay. It could be if it is x squared, if it is x squared, if it is x squared, right? So it could be looks something like that. So this could be okay. So meaning if I restrict to this line means what? Restrict to this line. Yeah, restrict to this line here. We can think of it as a slice. Yeah, slice. That slice. How do you look at that slice? Do you remember calculus 2? Do you remember, no? So if you have a parametrized curved surface, right? Okay, we can look at the intersection between the plane and that variety. Okay, so the intersection exactly is the substitution. Okay, so along this line, how this variety looks like, along this line, how this looks like. Okay. Okay. Any question? No question? No. Okay. Feel free to ask. So next definition is P is called a smooth or regular point. And so we're going to define smooth point now. Yeah. Have a surface P if there exists some I with del f del xi p is not 0. Okay, as long as there exists some I such that del f over del xi p is not 0. So at least in one direction, is the partial derivatives is non-zero. But this one only restricted to hypersurface. Later when we define for general variety, it's a bit different. Okay. For hypersurface, you just need at least one. Okay, the number at least one here is quite important. Correspond to the one function inside to define your hypersurface. Okay, this two number one is quite important. So otherwise, P is called the regular point or singularity. Okay. Okay. Yes. As long as this, I guess you cannot check, right? Does this means what? You cannot but this one is polynomial. What do you mean by does it exist? This is polynomial. Okay. Yeah. I think for polynomial you cannot doesn't exist.
Maybe for the square equals to
Y squared equal to x cubed and then
just
y squared equal to x cubed. Okay, then the origin, sure. Yeah, which one you want to compute both? Compute both? Okay, so if let's say this is f1, so del f over del y is 2y, del f over del x is minus 3x squared, and the origin is 0. Yeah, doesn't exist is like analysis problem, right? Left-right limit doesn't exist, so you cannot partial differential. But here is polynomial, so you should go with differential rule. Yeah. Okay. The remark here is so from here, what can we see? Actually, what we can see is P is a smooth point of V if and only if TPV is an affine hyperplane. Okay, so actually there is a equation, okay, that govern this point, okay, on TPV. But if P is a singular point, the partial derivative polynomial is just a zero polynomial, right? So it means what? What point satisfies zero polynomial? All points. So meaning your TPV actually is everything. Okay. If there's one non-zero element at least, then there's a equation that governs your zero set. Okay. If no, then every point is a zero set. Okay. So what you can see here is if you are a singular point, right, then your tangent line actually live in everywhere in the space. If you are smooth point, your tangent space is quite restricted on the R5. You could call it hypersurface, but in this case it's a plane, so because it's defined by one function, right? So actually it's a hypersurface, but in this case it's actually a plane, so they call it hyperplane. Okay. Hyper meaning we are at different n. If the n equals to 3 or 2, 3, right? Plane in R3. Okay, so that's so good. Yeah. Okay. Next proposition. So if we start with an irreducible affine hypersurface, okay, if we just look at all the smooth point, V smooth here, okay, let's call it V smooth. So these are all the points such that your TPV is an affine plane. Okay, so V or U, let's pick one. Pick V. Make it V. Okay, this set here is open and okay. So you see throughout this course, or you always see open dense, open dense. What does it mean? Open dense. Open dense. Huh? What do you mean by open dense? Sorry? Zero or some problem. It's called open. Is that open or closed? Both. Both. Zariski closure, right? Sorry. In Zariski topology, what are the closed set? So Zariski topology are specified by closed set, right? So what we declare as closed? If as long as you are zero set of some polynomial. Okay, so those are the closed set. So in this case, in this topology, what are open then? What's the relation between open and closed? Complement, right? Okay. Make sense? Okay. So so the complement of V smooth should be closed. Okay. Dense? What does it mean by dense? Here actually refer to Zariski dense. Okay, so what does it mean by dense? Yes. So the whole space here is V. Okay, so meaning you just need to add some more thing to make it the whole V. Okay, so actually this set you can imagine is quite large. When we say open and dense, it always means that that set is actually quite large. Does it make sense? Because dense means what? As long as you add in all the limit point, you will get the whole space. Okay, actually quite large. Okay, so meaning from this proposition, you'll see that actually smooth. Actually, most of the point on your variety or the hypersurface for now is smooth. Most of the time. Okay. Most part of the variety actually is smooth. Okay, only certain part is singular. Okay. Right. So let's look at the complement then. Of V smooth here. Okay, the set of V Seng here is V take away V smooth. Okay, so what's this? Oh no, what's this? We write it as a zero set or something. So you see, V smooth is what? Here is only logic, no algebraic geometry, logic only. So if it is smooth, there exists some I such that partial f over partial x p is non-zero. If it is singular, otherwise means what? For all, okay, for all I, where this partial f is 0. Okay, so actually, this V actually is a V of partial f of x1, partial f of x2, and until partial f of xn. There's one more. 0 side is satisfied. Huh? P picking from where are these? We're going to pick this. Yes, f is servicing there. Okay, so meaning V singular is actually a 0 set of f plus all the first partial derivative. Okay. Yeah. So maybe if you very pedantic, you can try write down the equation, the equality of this set. But if you got this, then it is obviously true that V Seng is a closed subset. So that V smooth is open. Okay, so next part, we need to show that it is dense. But not that V is irreducible. Every open set in an irreducible, every open set in an irreducible set should be dense. Okay, this is something that we proved before. Okay, but then we need to make sure that this V smooth cannot be empty. That's it. Okay, because we already show open already. Okay, so since V is irreducible, we just need to show that there's something inside. No. Or, in other words, we can show that V Seng is not the everything. You cannot be whole line to be singular point. How do you draw that? I don't know. Can you draw it, Chiwi? Can you draw it? Draw a variety such that every point is a singular point. Can you do it or not? Can you do it? Huh? I mean, if that should ask you if there exists a variety such that every point is a singular point. You can imagine, right? So now we're gonna prove you it cannot happen. Okay. So if V Seng equals V, okay, then all partial derivative should vanish from V. Should vanish on V here. So this implies that del F over del Xi is in the ideal F. Okay, because F is sorry, V is a 0 set of a principal ideal, right? Okay, so if V is equal to V, then you should be able to get all your partial derivative from it. But since degree of partial derivative should be strictly less than degree of F, okay, this is a polynomial, just polynomial. But then can you generate a lesser degree polynomial now instead of principal ideal? You should use the division algorithm. Those degree F should be the minimal degree of ideal, right? Okay, so if you have a less, I mean, a lesser degree polynomial, this means what? The remainder here should be 0. Okay. This is AA1. Makes sense or not? You can ask if you learn. Okay. Using a division algorithm, then the lesser degree will appear in the remainder part. But if your remainder is non-zero, then your ideal cannot be the principal. It's not divisible. So you remember must be 0. BD is 0. Okay, actually there are two cases here to take care. This is the thing that we didn't spend long time talking about. It's about characteristic of your field. Okay, so there are different treatment here. So you could imagine, what could you imagine here? The easiest case is you see that first you hope that if the first partial derivative is 0, then you should imply that your f is constant. Is it true in the normal calculus class? If your first derivative is 0, your f is constant. Okay, actually this one rely on your characteristic k to be 0. Okay, so there are infinitely many elements inside your field. Okay, but if your characteristic k is finite, then what could happen? What's the thing that evaluates 0? So let's say characteristic of k equals to p. P is 0, right? In particular, p times some monomial is 0, right? Okay, so could it be a non-zero f such that the first partial derivative to be 0? Can you imagine? After the differential, there's a p coming out. SIP, SI to the power p. Okay, SI to the power p is not constant. Okay, but after you differentiate, p comes down, right? Then we got p minus 1. Then that p goes to 0. So 0 times that monomial is 0. Okay, so there's some non-constant, okay, f that evaluate to 0. But what? But there's some trick here that I'm not going to prove also. So if characteristic k equals 0, then this is the normal case. Follows that. Yes. What's the characteristic of field? Meaning, let me think how to phrase this. There is a injection. So if it is a characteristic 0, meaning there's an injection of z into the field, and then finite one is set p into the field. Injection. How to phrase it? Okay, the easiest way to think about it is okay. Let's talk about finite characteristic first. So if it is finite characteristic, then p is mod 0. I mean, yeah, p mod p 0. I mean, like mod p 0 mod p. So you consider everything mod p. Is it a proper method of this? I remember we used the injection to talk about it right last time. Yeah. So what's the injection again? Is it? I think it's z. I think it's from z p to k. Is injective. Yeah. Because k cannot be injective. Cannot inject to smaller field. What's the definition? Anyone can search. Huh? Yeah. Oh, okay, yeah. Kernel of z equals to, yeah. Okay, that one makes more sense. I mean, kernel of z, then after you mod out by kernel is injective, right? Okay, good. Yeah, luckily. Kernel is generated by. Yeah. Okay. So then it follows that f is either constant. Actually, if you really like, actually these require proof also. But it's very routine exercise. Okay, but yes. Okay, so since A is algebraically close, we actually can write f as g to the power p. Okay, so why is it true? So let's think about this. So if you consider, let's say, a plus b to p, what do you get in characteristic p? This is a binomial extension, right? Okay, so it's a sum of p what? P plus p. What's the sum here? P 出现了 or a to the n, b to the p minus n going from 1 to 0 to. Yeah. So if you notice, if you write down this p over n, right? When your n go from 1 to n minus 1, right? What can you see here? So if you expand this formula out, there's a p factor inside there. Okay, all the middle term, there's a p factor. Okay, only the first and the last one you can solve p. Okay, so meaning what? Meaning just put that. Then this is just AP plus. Okay, so the nice thing about characteristic P is this thing. The middle term all disappear. Then this is the exact mistake that a common high school student will do. Actually, they are quite advanced. They work in characteristic P. They straight away bring the P in. There's a name for this map. This map is called Frobenius map. Okay, makes sense? Okay, but there's a contradiction if you can write it as a product of G, because F is assumed to be irreducible. Okay, so there's a contradiction. Yes. Okay. Any question? Any question? Before we break. Hey. 这个，你开啊，你 expand 啊。There will be a factor of p for all the middle. Only the first, because first you got a p factorial again. The last one then you also got a p factorial again. So the p at the top and bottom will cancel. But in the middle then you won't have p coming out. Right? If n equals 1, this p minus n becomes p minus 1 already. There's no p. On both denominator term here, there's no p. When n equals to 1 to n p minus 1. Write it down. Please write it down. Yeah. Oh, for f is the constant means what? If the constant is non-zero, then your 0 6 empty. If the constant is 0, then your variety is everything. For contradiction, huh? For contradiction. If everything for contradiction. If everything got contradiction. Any contradiction if V is 0. If F is 0. Irreducible. It's not irreducible, right? The whole space is not irreducible, right? Is the whole space irreducible? Is it? Let me think. Is the whole space irreducible? No, right? Not every two open set is empty intersection, right? The whole space shouldn't be reusable. Can everyone go and check? Or maybe I make my claim first. 有疑问有没私说吗 ？Okay, so ANK is it? So why? Can you say why? That is prime. Yeah. Okay, so try and write this down. Whether this claim is true or false. Now we can discuss this. If this is false, right, then think why there's a contradiction. P 从哪里？